All right, so today we're going to hopefully finish up with our discussion on collections. Remember, this is chapter 7 from the book. The book goes really fast, so we're probably going to go through sections 2 and 3 today, and it's a lot of slides, but that's because there's a lot of material to cover to understand. Where did we leave off? Wasn't it over here?
We talked about linked list.
Linked list. Yeah, here we go. Didn't we just finish the comparison of linked list? And why adding to the start of a linked list and the end of a linked list, why is that considered fast?
Just gotta draw arrows.
Because you draw arrows. I love that explanation. That was beautiful. Do I have yeah. You just draw an arrow. You put a box over here, put an arrow, or you put a box over here and put an arrow. And that's all we care about in this class. When you take data structures, we're going to go into far more depth about what that is. You really want to know, I can answer how all that works. But what was slow about linked lists? Anyone remember? That word slow up there a lot. What was slow about the linked list compared to the array list?
Getting the index of something?
Getting an index, yeah. Get is slow. Because get an index, you have to iterate through the whole linked list. Great. So then here's what you may think of when using a linked list is you want to print out every element of a linked list for I equals 0 to the list size, I plus plus, element, list.get, and then print it out. So the code executes O of n operations, get every time. In other words, what that's saying is if you assume n is equal to the size of the list, how many times is get called?
N times?
N times, right. If we define n to be list.size, then it takes O of n operations, O of n times to call, we call get, I should say. But when you call, what's the big O of get on a linked list? Whoop. Is O of n, right? So every time you call get, it's an O of n, and you're calling get n times, so it's really O of n times O of n, which is n squared, which is much worse. Good read. Much worse than O of n. So in other words, this code will take prohibitively long to run on large data sizes. I think I touched a little bit on a solution here. Does anyone recall what it is?
Binary search.
No. But that binary search can't be done on a linked list because you can't just jump to the middle and go around because it's just a list with a lot of links. So can't do it that way. If we're going to go through every element of a linked list, does it have to take n squared time? Can't you just go one, then the next, and the next, and the next? Okay. What we used in order to do that was something called an iterator, if y'all recall. It's an access method regardless of underlying structure. It's very generic. It's usually, lightweight, whatever. Basically, the idea of an iterator is that if you have a list and you want to iterate through every element, you use an iterator to do it. Every container, by the way, a list is a container, and therefore an array list is a container, and a linked list is a container. All of those can give you an iterator, and you just call .iterator to return an iterator. You get the next object with next, and you set there are more objects in the sequence. Basically, you ask if there's more objects by calling as next, and you can remove the last element returned by iterator with remove. All right. That's confusing. Let's actually code it so it makes sense. Oh, I didn't load up IntelliJ.
How'd you come up with your computer's name?
Shiloh?
Yeah.
Oh.
You just liked it?
No, I think I was just, at the, what was it? When I was in California, I was going to church there. There was a family that had 4 kids, and one of them was called Shiloh. And he was very talkative and a lot of fun. And then I noticed I liked the name Shiloh, so I named my computer that.
Is your computer like a child too?
Yes. You know, not exactly the...
It's probably more obedient.
It's very, okay, true. Well, kind of, right? because it does everything you say very literally.
It tries to.
And it's got plenty of energy, that's for sure. There's no denying that. Yeah, it tries to do exactly what you say, but it doesn't always do what you mean. All right, so wow, we got a lot of code now. Okay, let's close some of these things. We did array funds, student, list example, player, game loop, pane. All right, good, we're clear. We've been met. Ooh, good, list example. So if we're up here, we got some list basics. All right. Let's create another quick little function. We'll call it list iteration. Iteration. Public static void list iteration. Okay. And I'm going to copy this down. And what this does, create a. Actually, let me ask y'all, see if y'all are paying attention. Can someone tell me exactly what this line that my cursor is on does?
Creates a pointer to a list.
Creates a pointer to a list called,
Item.
it's not just a list, it's a list of integers. All right, then what does it do? Oh, actually, hold on. Where is that pointer created?
Under the heap.
No, stack. On the stack. There we go. Then what does it do?
Created it, right?
No, it created the
Oh, it
pointer.
initialized all the values, right?
Hold on. It created the pointer called IL on the stack. So that is what this does right here. Creates a pointer called IL on the stack that points to a list of integers. All right. What else does it do?
Makes it an array list?
No, because you have a pointer. You haven't. What do you need?
I'm not sure.
What happens next? What does new array list do?
Oh, it creates a new object.
Creates a new object of type
List.
array list.
Array list.
Array list. Where is that object created?
The heap.
On the heap. And then once that object created, it returns a pointer to it. And who stores that pointer? Where's that pointer stored? In
Stack.
right on the stack.
Yeah.
What variable's holding it?
IL.
IL. There we go. Hopefully you were able to follow that. Important to keep that in the back of your mind how this is actually working. Why is it okay that IL, even though it's pointing to a list of integers, can still point to an array list of integers?
Basically because it's, there's something from solid, right?
Close. But what's the relationship between list and array list?
An array list is a list.
The array list is a list, correct, which means that the list is a parent of array list. In other words, array list implements the list interface. Please make sure that you fully understand what's going on here. It's going to be vital not just for this class, but when you go into data structures, it's going to get way more complicated than this. Okay? I'm trying to help you out by getting the basics done right now, because when you go to data structures, it just goes on. All right, so fill out the list with some random values, random numbers. All right. So this creates a for loop from 0 to 1,000 and basically stuffs the array list with a bunch of numbers. Okay. Now, with an array list, if we wanted to find the sum of all those numbers, what would we do? Probably create a long sum equals 0, and then what would y'all probably do next?
Well, is there
Right,
an
throw
array
it.
list dot sum?
That's a great question. Let's find out. IL dot. That is always the best thing to ask first. There's a sort.
There's also an add, so I don't know. Well, that'd be
No,
add,
we already add.
Yeah. So
Nope. We can't just call sum.
iterate through it.
Iterate through it. How would y'all like to iterate through it?
For loop.
For loop. All right, let's do the for loop. So for int I equals 0, I is less than 1,000. Actually, we should do list.size or il.size. IL is just the integer list, I plus plus, sum plus equals IL dot get of I. Right? And I'll just go down here, system.out.println, sum is plus sum. All right, let's go ahead and run that real quick, see if it works. Sum is, that does make sense, because there's probably a lot of negative numbers. So let's get rid of the negativity, because we don't want the negativity here. So we'll make those random numbers be absolute values, which makes them all positive, and then we'll run it again. All right, awesome. What if we want to use a linked list instead of an array list?
Just change array list to linked list.
All right. List. Okay. Now we're using the linked list. All right. Let's go ahead and give it a couple more random values. We'll try 10,000. I haven't done this in a while, so I'm just going to test. All right. Let's make it 100,000. Oh. It's taking a while. Whew. You know what? Let's find out how long that took. Long start time equals system dot, what is it, nano time? And then we'll get long end time equals system dot nano time. And then we'll put sum as this, dot out dot println, computed in, let's see what we have. It's a nano, and we want milli. So that's, what's that? Because it goes nano, then micro, and then mil. So we want to divide it by. Does it go seconds, milliseconds, microseconds, nanoseconds?
Yeah.
Right. So then we want to divide that whole time. We'll go ahead and make a long duration variable. Is start minus end. Oops, start time minus end time. So this will get the duration in nanoseconds. And then we'll do duration divide equals. So that would be in microseconds. 1, 2, 3, and that should be in milliseconds. Convert to milliseconds. We'll do duration plus ms. So let's see if that.
Space before the ms.
No, we'll go ahead and keep it just like that. That way it'll be connected. I should probably have end time minus the start time. Just going to throw that out there. And I don't think 687 milliseconds is correct at all.
That time seemed faster.
It did?
Yeah, than the first time you ran it.
Let's see, 1, 2, 3. Yeah, there's an extra 0 here. Yeah, now let's run it. Okay. Well, the second time always feels faster because you now anticipate that it's going to take longer.
I don't know, this time's taking long again.
You think so? So that took about 7 seconds. You're right, this time it did take longer. Let's run it one more time. Whew. No, 7.2 seconds. This has to do with what I'm talking about, that this idiom of calling list all this time is very slow. And just to bring that home, the array list, what's the big O of calling get here on an array list? O of, no, on an array list. On linked list it was O of n, but on array list, how when you go to an element of an array,
The index?
yeah, the index of an array, do you have to iterate through the whole array?
No.
No, you just jump straight to it. So that's O of 1. So if we run this with an array list, ooh, 9 milliseconds. See? So it seems like the array list is winning here, but the real problem is we're not using the linked list properly. So I'm going to comment this out real quick. What's the other way we can do it? Well, we can create an iterator. Iterator on, we'll say integer. I'll call it it for iterator equals il.iterator. That's going to get an iterator from that list, whether it's an array list or a linked list. And now we're just going to do while iterator it.hasNext, while it has an element, sum plus equals it.next, which is the next element. So while there's something in the iterator, go get it, add to sum, and then see if there's anything else left. So we go into this simple loop of going and testing does this element exist? I mean, is there something else to go to? Y'all see what I'm doing here?
So for a linked list, we need to do iterator. And for array list, we can do the get thing.
Well, we can also use an iterator here for an array list. I'm just asking, do you understand what the iterator is supposed to be doing? So if I run it with an iterator, 6 milliseconds. Wow, that was even faster. But this is an iterator on an array list. Now if I change it back to a linked list and I run it, back to 7 milliseconds. So what am I doing here?
Saying that using the iterator is the best way to.
Well, at least it's a better. Why is iterator better?
It's faster.
Okay. It's faster. Why is it faster? Don't know? Do you know how the iterator is going through your data structure? No, you don't. That's being hidden from you, right? You're just adhering to an iterator class. So that means that the developer of the iterator can choose their own implementation to quickly iterate through your object.
How are they doing it?
Whatever they believe is the fastest. It's being hidden from you. It's being, and what is that? Ooh, which O principle is that?
Someone like about the toaster, or like we see the toaster, but we don't need to know how it works.
Yes, that's the right analogy. And the term was encapsulation, because they're encapsulating or hiding how the iterator actually does the iteration from you. So the question is, should we all use the standard for loop when we're using a list, or should we use an iterator?
Iterator.
An
Or a
iterator.
linked list,
Hmm?
right?
You should use an iterator for
Linked list?
all of them.
Oh.
In reality, you should use an iterator for all of them. Because then, whether you're using a linked list or an array list, it doesn't matter. I mean, I put an array list back in here. You still get the same performance out of it, and you don't have to change your for loop code. You're just using an iterator.
You take it out. Oh, you're talking about the top one.
Yeah, that's just to add elements. I'm not calling .get. I'm not iterating. That for loop, the question was when we fill it out, why don't we use an iterator? Because I'm not iterating through the list, I'm adding elements. So there's nothing to iterate on. But now that I have my list, there is something to iterate on. Okay. So iterators, in Java it is accepted that you really do want to use iterators as much as you can when you wish to iterate through something, because then the underlying implementation can actually handle how you go through the list, whether it's an array list or a linked list. And when you go into data structures and you find tons of different data structures, again, the iterator, the way it's iterating is hidden from you. You don't care. The maintainer of your data structure can do that for you. And usually they've been coding it a lot more than you have, so it's probably well tested, and they've probably done some performance tweaks as well. All right, so we talked about how the iterator works. So that's at least pictorially, if we're doing an iteration on an array or just a list, maybe your iterator is pointing here, and then when you call next, the iterator jumps over to the next position and returns this element. And then if you call next again, it's going to jump over to the next element and return this element. Does that make sense? So it's just jumping and returning. That's how it's working pictorially. Whether this is a sequential array or a linked list is irrelevant. That's just how the iterator does in the background, but what's happening in your mind is what's important, because it's going to start at what's at the beginning of the list and iterate through it. You can actually remove if you want to. So what solid principles does Iterator provide for a list, array list, and linked list? What's the first easy answer?
Single responsibility.
Right. When in doubt, just single responsibility. All right. Why is it here in single responsibility?
The iterator?
Yeah.
It has one job.
One job, and that's to iterate. It doesn't do anything else. That's all it does. All right. Great.
Its purpose.
That's its one purpose. Fulfills that one purpose, and we're good. All right. What else does it adhere to?
Encapsulation.
Okay. Yes. Encapsulation, which isn't part of solid, but correct. Encapsulation.
Oh, what's the dependency inversion principle?
Dependency inversion principle. All right. So that's saying that you're adhering to an interface. Correct. Because an iterator is actually just an interface, and then you can connect which implementation. If you're doing an array list iterator or a linked list iterator. That's good. That's a good example. Those are the big ones. Really, the thing about L, remember that's the duck principle, and that's is the list iterator only dealing with iteration and nothing else, is really what that one's trying to explain to you. So you can almost always say that one as well, unless it's really messing something up. See, integration, or segregation principle, there we go. Wow, that was hard to say. Yeah, that was fine. Simple implementation, open close principle. Well, yeah, that goes with dependency inversion here. All right, so it's actually adhering to a lot of solid principles, which is great. All right, benefits: speed up loops over linked list elements. Why is that? Why is the iterator on a linked list faster than using our for loop?
Because
They made it that way.
Goes to the next
the
element.
yeah.
It just goes to the next element, and if you do for loop, you have to start from the beginning and go all the way up. So the iterator just keeps track of where you are and moves forward. All right. All right. Provides a unified way to examine all elements of the collection. What does that mean?
If you have like different data types, right?
Right. Data types. You still have just one
Object.
way of iterating.
So if you have like different objects.
Yeah.
like,
Yeah. Yeah, every collection has an iterator method. In fact, that's the only guaranteed way to examine elements in any collection. Ooh, why is that? Well, in order to really answer that question, you need to Google Java collections. And collections. Actually, it should be collection, I believe. Well, that's really long. Okay. Well, if you look at the list of functions that a collection has to implement, there is no .get. Okay, this is the wrong collection. There we go. Okay, much better. This is the right one. So you can add all, clear it, ask if it contains something, ask if it contains everything, ask if it's equal, find the hash code, is it empty, return an iterator, remove, retain, size, to array. So really the only way to actually go through it is to just call .iterator. I mean, I guess the other way is to call .toArray and then go through the array, but that's way more work than what's needed. So the reason for that is the interface collection only provides iterators, an iterator as a way to go through it. And so the point here is when you start thinking about lists, it's best not to use indexes unless you need to. just think of using iterators to go through a list. Because a list, in reality, is you want to have a collection of objects that you need to run through every once in a while. That's the point of a list. If you need something else, you need to use something besides that list. As you can see up here, we're going to have sets, hashing, and maps. Okay, I started on the summary. But yes, a list is keep track of items you wish to iterate through. That's what a list is very good for, or used for in Java. Array list is rapid random access in case you need to jump around it, but it's slow when inserting or removing in the middle, or in the beginning, in the front. A linked list is optimal as long as you're doing sequential access, aka you're not trying to jump around in the list. Fast insertion and deletion, you can add in the front, add in the back, get in the front and the back, and it's really fast. And it can be easily used as a stack or a queue. Have we done stacks and queues here? I don't think so. No, that's fine. Basically, a linked list is a pretty good candidate to implement a queue or a stack. That's just another type of data structure.
That's how that word is pronounced? Q?
Queue.
It's like Q U.
QEU?
Oh yeah, I learned that from playing Roller Coaster Tycoon.
Okay. Oh yeah, you gotta put in the queue. It's a line. We call it line here in America, but it's a queue. A quay? A quay?
It's not, no, yeah. It's just like people back home pronounce it, the quay.
The quay?
Yeah, like it's not.
I'm,
How do you say it?
if I had to take a guess, that's probably a French word.
It's
If I had to take a guess. All right, I'm going to go ahead and pause recording here because that finished up with iterators, and I think then going into sets is a good next topic.